proceed. We can start. So the recording is on. Okay, go ahead. We have a question related to the last lecture. If you would like, instead of typing, oh, okay, it is already. Okay, I think the answer to your question will become clear in some time, because actually neural networks, they work asynchronously, and they work in parallel, and to enable this, we to make a real copy of neural networks, we would need to create a hardware that looks like real neural networks. And obviously, we are simulating neural networks on computers. So it is not that obvious how to provide that all components of a network really work in parallel and asynchronously. But I think it will become more and more clear as we proceed. We will be talking about a very particular architectures of neural networks. And these architectures, they somehow eliminate this problem of asynchronous and parallel operation. But just let's wait. I think it will be clear. It will become clear. So let's begin with a very brief. Okay, thanks. Let's begin with a very, very brief summary of what I have told you before. I introduced you a neuron or artificial neuron, and this artificial neuron, a block diagram is somehow trying to depict what happens, how this unit transforms input information, which is a vector, into output information, which is a scalar. So Y is the output, and it is related to the input via a nonlinear transformation. So if I would like to express it mathematically, this will be this transformation. And F is some nonlinear squeezing function, and this squeezing function is justified by an attempt to mimic one of the basic properties of a physical device. A neuron is a physical device, so its output signals, they are either the minimum ones or zero. Neurons are either mute or silent, or they send information at some maximum rate. That means it needs to, the output domain of the output value has to be restricted, limited. And this function is trying to provide that. This is a function of a state of a neuron. So basically, note that this is a state, and the state is a dot product. And the dot product can be any real number, because a dot product is what makes neuron analyzing input information in some particular way, depending on its weights. And this modification of different inputs using weights, these modifications, they produce chunks of information that gets accumulated, and this accumulated influence of input x vector forms a state, and the state is transformed into the output. Mathematically, probably the most commonly used nonlinear function is a logistic function. And this logistic function, I can make it a little bit more complex by adding a parameter. Let's name it beta. And this beta is a parameter that can control a slope of this sigmoid. So if I increase beta, then my sigmoid function becomes steeper and steeper as I'm increasing beta. And at some limit, I might get a step function as a nonlinearity. And a neuron with a step function, so this is a possible also form of an activation function for a neuron. So if this is a state and if this is output, a possible form of this output nonlinearity is just a step function. And a neuron which has this particular type of nonlinearity has a name, and its name is perceptron. So perceptron is just a name that has been assigned to a neuron with a very particular form of this output or activation function. A step function is not very convenient because it doesn't have a derivative. So one of the most important elements in the theory of neural networks is how to update weights, how to find appropriate weights. And the formula for that, so if I have a weight vector, and I would like to make corrections to this weight vector, this is subject to something that I named a delta rule. Delta rule was the way to compute what is an update given input sample. So basically, this delta rule had this form. So that was a form of a delta rule where I was trying, and the delta rule was a way of iterative training of a neuron. It means finding better and better weights so that input examples get correctly classified if my neuron is used as a classifier. So here this delta is an error, is a difference between, so this delta was a difference between what I expect at the output and what I get at the output. What I get at the output is just this nonlinear transformation. So this is a transformation of a dot product. And if I have a function that is differentiable, like logistic function, then I know that this f prime for a logistic function is just a product of y times 1 minus y. If this is a perceptron, this function is not differentiable. However, people assumed that as we need to put something here, what has been adopted for a perceptron is just to put a constant value, as if this neuron's transfer function as it is linear. What is a justification for this choice? The first is that it is very simple. And the second, it is still reasonable, because it means that if I am making updates, they will be just proportional to my input x, just proportional. And it ensures that I'm making steps in right direction. I'm here when I'm using a logistic function. This derivative is something that also controls a range of the step. If something gets okay, if my output is close to the saturation values, then most likely any changes are not that important, because it means that probably my neuron already stabilized. So this derivative is providing me a mechanism for reducing a role of a change. For perceptron, we just assume that a derivative is, we say it is just one. And I am just mentioning this perceptron, not because it is used right now. It is not used, or it is used very rarely. It was historically the first model of a neuron. Historically, the first model of a neuron was a neuron with this step nonlinearity, not a logistic nonlinearity. And the second thing why I am introducing this name is that certain architecture that is composed of several neurons and is very regular has a name that uses this term. But I will comment on it later. So if I am still with this variations of a neuron, variations in a model of a neuron, basically they concern this nonlinearity. So I presented you with two nonlinearities. The first is the squeezing function, this logistic function. And this logistic function is a function that transforms real numbers, real values. So S belongs to real numbers, and I'm transforming this within an interval 0, 1. So this is logistic. This logistic function does that. Logistic nonlinearity or logistic activation function. Now, if we have this perceptron, what is happening is that given a state, which can be a real value, I am just transforming this into a binary number. Perceptrons, they were considered. One of the reasons was that it is a natural for data classification, natural representation, because I have either 0 or 1. That means that something either belongs to class A or it does not belong to that class. In case of logistic function, I'm getting real values. So I might say that from the one point of view, it is not that obvious as we would like to it to be, because a result of classification, we would expect that the neuron says yes or no, and it is saying maybe. But from the other perspective, maybe this is a good outcome, because I might also tell that a result of classification is a value that also gives me some more information. How certain am I that this sample belongs to one class or to the other class? But these are not the only candidates for activation functions. And I begin with the ones that were used traditionally. And later on, when we move to deep learning, I will introduce other concepts. So the two more that I'm going to just introduce are functions that convert state that is a real number into a bipolar values. So values that either are from the range from -1 till +1, or in the second case, so this is R1. That means this is a real number. And the second example or a second form of this activation function will be a function that produces a binary pair of values, but this time bipolar. So a difference is now just a very tiny difference. It is just a change in a range of output values. So the first type is, for example, hyperbolic tangent. So y is just a hyperbolic tangent of S, and this is just a simple sine function, sine sub S. So the second, this second or this latter value will be just the function that assumes either 1 or -1. So these are counterparts of a logistic and step function. People were using these bipolar functions when they were analyzing particular applications of neural networks. For data classification, it is not used, but it is used when we are talking about some networks that might have feedback, and they will try to maybe remember some state. And then if values of neurons in a neural network are bipolar, it is much easier to perform several computations. When these values are 0 or 1, it is not that easy or not that simple to realize certain transformations. Obviously, in the second case, when I'm talking about bipolar values, so here a difference is that now I have bipolar values, output values of neurons, and here I had unipolar, so it was just positive numbers. So bipolar are not physically feasible. Obviously, these bipolar values is something that diverges from the biology, because we don't have negative, nothing like negative activity of a neuron. But later on, you will see that we are diverging from biology, and in deep learning, we just diverge without having any problem with that. This will be common. It was just a short extension of information about the neuron. But once again, I will write it once again. A neuron is just a mathematical device or transformation that converts input vectors into output scalar values. And what is the most interesting about neurons is how to update its weights using examples. So once again, I will write this delta rule, because these two equations basically summarize everything that is really important about a neuron. And now let's get back to geometrical interpretation of neurons' function. So what I showed you is that if I will have samples that belong to different classes, to two different classes, like red and blue, using this delta rule, I can learn how to separate these classes using a line, because a dot product is a linear operation. So this line will be determined by weights that I can appropriately choose using this delta rule, this training procedure. And the training procedure will be iterative. So I will be updating weights maybe after presentation of a single sample, or maybe I will use this mini batch approach. We are talking on machine learning that we have a few possibilities on how to train our algorithms. So I can either train this neural network using consecutive samples, or I can train this using mini batch approach. And if this is a mini batch approach, on the right hand side, instead of a single X, I will just put a sum of a few X's that create such a mini batch. So I can do that. And one more thing that I would like to just show you is that if my input values are binary, so basically here I wrote you, I made a drawing where my inputs were some real numbers, but I assume that all values in a neural network that are produced by neurons or that are used at the input are just bound to this interval between 0 and 1. So here are just some values that are real, and here I show you that if I have binary input values, I just have 4 different possibilities, and in 2-dimensional case, and the neuron, again, if for example this sample belongs to a different class than black samples, then I can, or maybe let's make this blue. So in this case, I can also find or train a neuron so that it correctly separates these samples. And one of the conclusions that we have already came to on machine learning was that if I have an expression that involves a linear combination or a dot product, it means this is a linear combination, linear in a domain of parameters. So if I am not assuming anything, if I'm not making any transformation of input vector, then the only thing that I can do is to solve linearly separable problems. And at the end of the last meeting, I just recalled this, that this is a very severe limitation if I would like to process input data using dot products with vector of weights. What I can do is I can solve a linearly separable problem. And linearly separable problems are trivial problems. So basically, if I would like to use a neuron to solve anything more interesting, it will fail. And one more thing that I just want to add now, if you look at this example, again, this is a linearly separable problem. But this linearly separable problem for binary inputs, I can tell that this is a problem of computing a logical AND or logical OR, depending where is 1, where is 0. And I can always separate one of the vertices or one of these points from the remaining ones. So I can always, one neuron can always realize or implement a logical function AND and obviously a logical OR, regardless of which point is red. Yes, it doesn't matter which one is red. So if this one is red and these are blue, then obviously I can separate one from the others using a line. So I can always separate one vertex from the remaining vertices using a line. So AND and OR are linear operations. So AND is just a linear operation. That I'm focusing on AND. Is a linear operation. So a neuron can do a linear operation. It can correctly respond and compute a logical product of inputs. And keep this in mind, because in a while it will be important. So we have a neuron. So where did we get so far? We have a neuron, and the neuron is a device that can solve trivial tasks. So the question is whether we really can benefit from such a device or such an algorithm, depending on how do we look at a neuron. We can look at this as at an algorithm, or at a system, or a device. But it seems that it is not very useful. Now, you recall, we are talking about logistic regression. That was a method of classification that was basically almost identical or identical to what we have to a function that a neuron performs. So in logistic regression, we have exactly the same formulation on how to make a classification. We are just computing a dot product. We are wrapping this dot product in a logistic function, and depending on a location of a point with respect to parameters, we could make a decision whether this point lies above a line or a hyperplane, or below. So we were able to make a decision to which class this point belongs to. And we were able, obviously, to find parameters of this hyperplane or of this line. And in logistic regression, again, we had an iterative procedure. So basically, I'm sorry. I hope you could stand it. Up to this point, logistic regression and the neuron are pretty much the same. This is nothing really new. Just an artificial neuron is trying to replicate something that exists, whereas logistic regression was a purely abstract concept. And how we were trying to solve problems that were a little bit more complex than linearly separable ones in logistic regression. So in logistic regression, when we had a problem that I introduced during our previous lecture, I introduced a problem that is not linearly separable. And I named this problem as an XOR problem. And I'm able to solve this problem using logistic regression, because in logistic regression, recall that I could try to appropriately transform input variable by adding more terms, and this input variable after this modification or after this transformation were an element of a dot product that corresponded to a polynomial of some higher order. So using logistic regression, I could, for example, find a second-order polynomial that would separate the samples from a red class from samples from a blue class. And we are able to solve more complex problems. How neurons and how do we try to approach this problem using neurons? Well, it is not the same. It's a different way. And the way that has been adopted in neural networks is some obvious extension and obvious adoption of a knowledge that we have. Because our neural systems, they have multiple neurons. We do not have single neuron, nor isolated neurons. We have neurons that are connected to each other. So let us assume once again that our problem, the problem that we would like to solve, is this XOR problem. So basically, we have members of two different classes, and these members are not linearly separable. So how can we solve this problem given neurons as our algorithms for data processing? The first one thing I'm recalling, obviously you see that there is no line that there's no single line that I can draw to correctly separate these samples. But if you think a little, you will see that, but I can find a line that could separate blue points from the first cluster from a red. And if I forgot about this part, I can say I can solve this problem using a neuron. So if my input, this is my input, these are x1 and x2. So if I have input x1 and x2, I can say, okay, if I have one neuron, and if I try to train this neuron somehow, or on this data, what I would get is I could get an output value that indicates correct solution of this sub-problem. Now this is a sub-problem. And there is a second sub-problem. This second sub-problem is a sub-problem of separating between red points and members of the second cluster. So this is my second sub-problem. And I can solve it using a neuron because it's linearly separable. So I can say, okay, I might create a structure that is composed of two neurons, and each of these neurons theoretically could solve a sub-problem. If I would like to see, so if my first neuron, let's assume that my first neuron here has some positive side of my line and here is negative side of my line. So in other words, if something is on the right-hand side, a neuron would respond 1. If something is on the left side of this line, the neuron would respond 0. And similarly, let's assume that this is again something similar. Let's assume that this is a positive side, this is negative side. So here is 0, here is 1. So if you now try to depict outputs of the neuron number, let's name this neuron 1 and this neuron number 2. If I would like to depict outputs of these neurons, I can draw again or plot the distribution of these outputs on a plane. Now, let's assume that here I have, let's assume for now that this is a perceptron. So I have just 0, 1, no intermediate values. So let's assume this for the explanation. It's easier if I assume this is a perceptron. That means neuron number 1 and neuron number 2, they both have these step functions. So what are possible responses of these neurons for members of a red class? If I have a member of a red class, the first neuron will say 1, and the second neuron will say 0. So if I would like to draw a point that corresponds to a response of these neurons to input sample from a red class, it will be located here. Now, what are responses to samples that belong to a blue class? We have two different clusters. The first cluster will be transformed into 0, 0. Yes, because a sample that belongs to this cluster is on the negative side of both the first and the second line. And the second cluster will be on the positive side. So that let's obviously this is 1, this is 1, this is 0. So the second cluster, samples from the second cluster will respond with 1, 1. If you look at this, what we have is we have a bunch of linearly separable points. So we have a bunch of linearly separable points. So if so, I can separate them with a neuron because they are linearly separable. So if I add here a neuron, what I can expect is that this second layer or neuron number 3, let's name it for now, neuron number 3. This neuron number 3 will be correctly responding to points that are non-linearly separable. So if I have a problem of this kind, my output neuron number 3 will be telling, for example, if this is, let's assume that this is a positive side and this is a negative side, so it will respond with 1 here and with 0 here. So the responses will be, if sample is blue, neuron, the second neuron will say, the third neuron number 3 will say 0, otherwise it will say 1. So this is a qualitative analysis. This qualitative analysis is something that gives us an idea on, first of all, that we can solve a problem that is not linearly separable using only linearly separable or devices that can solve linearly separable problems. So with neurons that can make a very simple decision, only to tell whether something is on the left or on the right of a line or above or below a hyperplane. If we arrange them appropriately, I can get now a network or an ensemble of neurons that is doing something which is much more interesting and which becomes something useful, because this is not a trivial problem. I might solve problems that are not trivial anymore. So first conclusion of this qualitative analysis is that we are creating a network. So that's the first conclusion. I can arrange appropriately neurons, and I am building a network of these units. Obviously, this will be a neural network, because before I introduced just a neuron, and here what we have is we have a neural network. So now this is something much more serious. The second conclusion is that it has a very particular architecture. The architecture is that the data flows upwards, and my organization of this network is that I have units here. Here I had 2 units, but maybe I could have 3 units or many units. And each of these units is trying to separate space with a hyperplane. So if I have, let's say, 4 different neurons, 1, 2, 3, 4, and if this is a 2-dimensional space, then maybe these neurons will separate space using lines or hyperplanes. In n-dimensional space, these are hyperplanes. So this is a role of these units that are here in this first portion of my network. And now I am passing results of this separation to a unit that is trying to somehow combine the results produced by the first layer neuron and how it combines it. Another piece of terminology. What I have is I have a structure that would look like this. I will have neurons here, and I might have neurons here. I might have more than a single neuron in this upper unit or this upper ensemble. I might have many of them, and data flow is that results of processing in neurons below are passed to neurons above, and all neurons below analyze input. So basically, the architecture can be summarized using such a drawing, and I can say that I have a layered structure. I have a first layer and of neurons. I have a second layer of neurons, and for now we just have 2 layers. And what is being produced by this network, if I have more, let's say M, if I have more units in this second layer, I will produce M output values. And what is an input? An input is just a vector that I'm applying to all input layer neurons at the same time. So my next conclusion is that I have something right now is just a 2-layer, but in general I will call that I have a multiple layer architecture. I have multiple layer architecture. Now, this multiple layer architecture, right now this is a 2-layer architecture, has one more property, and this property is that data or information flow is from the bottom to the top. So my input will be analyzed by the first neuron in the first layer, and at the same time, in parallel, it will be analyzed by the second neuron in this first layer, up until and up to the last neuron in this first layer. Let's say I have n neurons in this first layer, from 1 through n. And once these neurons process this information, they will forward outputs to second layer neuron. So this is a data flow, and the result of this processing is a result of processing of a network. So my data flow is unidirectional, and I can say that the network or the architecture that I have just introduced I can name it as a multiple layer feed forward neural network, because obviously we can arrange neurons in any way that we would like to. But here I have a very particular architecture, and I will be arranging neurons in a way that gives me some idea what this network of neurons is actually doing. I am trying to design an architecture that is very regular and that I will understand what it actually does. So what it actually does. I draw once again this architecture. So I have inputs, and this input vector is presented to my first layer neurons. So these are neurons of my first layer. So I will be presenting these inputs this way. And I have just told you that what are these neurons doing is each of these neurons is trying to separate space with a hyperplane, or to separate a plane if my problem is two-dimensional. If my problem is two-dimensional, my neurons, let's say I have a red neuron, so this is a red neuron, and let's assume that it is splitting my input space this way. I have a blue neuron, let's say here somewhere is the blue neuron, and it separates the space this way. And I have a green neuron, so let it be green neuron, and it separates the space, let's say this way. And what is a role of some second layer neuron? Let's assume that I have let's make it yellow. So I have this yellow neuron, and this yellow neuron, let's assume that we have just 3 neurons in this first layer. So just to make things simple, we just have 3 neurons here. And let's just to make things simple, let's for now assume that I have 1 neuron in the second layer. So what exactly is being done by this second layer neuron? Recall that what I am doing here is I am producing binary numbers, binary values. So 1, 1, 0, for example, or 0, 1, 1, or something like that. So what I can say is that a yellow neuron, if it operates on binary inputs, what it can for sure do is for sure this neuron can perform a logical AND operation. AND operation means that I am trying to determine what is a common part of the outputs that are produced by neurons of the first layer, because these outputs are responses that appropriately split a space. And AND means I'm trying to see what is an intersection. So let's assume that this is a positive. This is a positive side of green. Let's assume that this is, for example, positive side of blue, and this is a positive side of red. So what I can do, for example, is I can find an intersection of regions that let's make it yellow here. The intersection of 3 regions, and I can do that. For example, my neuron can respond to intersection of these 3 regions, because the problem that my neuron is solving right now, the problem is how to separate. I have now three-dimensional space, y1, y2, and y3, where, for example, this is y1, this is y2, and this is y3. And I have a binary problem, and this binary problem can be depicted as having a cube, and every input basically is every input can be viewed as a vertex of this cube. And if I am interested in this region here, so basically this region is a task how to respond to something that is inside this region. Is the problem of how to separate this one vertex from all the remaining ones. So I can say I can always separate this vertex from all the remaining ones using a hyperplane. I can always separate a vertex from the remaining ones. That means I can always perform AND operation. So the second layer neuron, what it actually is doing, it is extracting, and what are the regions? We have half planes. And we have an intersection of half planes. And intersection of half planes is a convex region. That's a property of geometrical property, that if I have half planes or half spaces that are defined by a hyperplane as one side of this half space, intersection of this half spaces is a convex region. So if I would like to explain what the second layer neurons actually are doing, I can say they are trying to identify or locate convex regions. And these convex regions, they just might be regions where samples from my class are located. So if I would like to solve a problem that is non-linearly separable, but has this structure of an XOR problem. So let's say I have two classes. So observe that basically what I'm trying to do is I'm trying to find a convex region that I might have many neurons. Here, what I have just drawn. I have drawn something that is the output of one neuron that is being provided with information by several neurons in the first layer. And my neuron, which is in the second layer. So this is the output of my second layer neuron. And these are neurons of the first layer. For example, this is neuron number 1, this is neuron number 2, this is neuron number 3, 4, and so forth. And if I would like to solve a problem Yes, I wonder whether you can hear me. Yeah, I'm sorry. My internet connection is not the greatest one, and this might happen. I hope you forgive me. Anyway, I don't have any choice. So, just to continue, if my network would contain two components in the second layer, so I will just type Y1 and Y2, and a bunch of components in the first layer, a bunch of neurons in the first layer. So basically, architecture will look like this, somehow like this. So what can I expect? Recording is still on. So what I could expect is I could expect that I will be able to correctly respond to samples that are located in some disjoint regions. So what I can hope is that I will be able to appropriately build convex regions for both areas or locations in space that contain red samples. And for example, this is something that will be covered by Y2, and this will be something covered by Y1. So as you see, this second layer, this two-layer structure, is a structure that gives me, in at least qualitatively, possibility of correctly identifying points that occupy convex regions in space. So this is something already useful. Obviously, we are talking in qualitative terms. The most interesting thing will be how to actually train these neurons to actually build these convex regions. But this is something that we'll be talking about in a while. Right now, let's conclude this part of this qualitative analysis with such a statement that a two-layer feed-forward neural network is capable of solving, and I will just informally tell, convex classification problems. So if a solution to a classification problem requires identifying convex regions in a space, then I can solve it using a two-layer feed-forward neural network. So now, what is more complex problem than a convex problem? Well, the only more complex problem than a convex problem is a concave problem. So what do I mean? The only problem that I will not be able to solve using this approach is the approach where, for example, I have this kind of distribution of samples. So let's say that I have, or maybe instead of doing something arbitrary, I will just show you something that is a very classical example of concave problems. And this classical example, this distribution, is called the two moons. That's a distribution of examples, which is concave, which is non-convex. I cannot solve this problem using two-layer neural networks just because samples that belong to a class, they occupy a region in a space that is not convex, but it is concave. So as you see, what I would have to do is I would have to, for example, separate space with this kind of decision boundaries. And unfortunately, this region is non-convex, is concave. So something that is more complex than convex is concave. So concave problems. How to solve concave problems? How to solve? Well, and again, in a qualitative way, this qualitative analysis gives us a very simple solution to that. Because let's assume that I have a region that is composed of, let's say, 3 different. So let's make it this way. So let's assume that I have decision region that is built by 4 neurons in the second layer. So this is Y1, this is Y2, this is Y3, and this is Y4. That means I have neurons that respond with 1 if samples are located somewhere here. All these neurons will respond with 1. And now, and these are neurons of my second layer. So I have 4 neurons in my second layer. So my network here has this first layer, and here I have the second layer. And now what I would like to do is I would like to make a decision. I would like to build or create a concave region. So this region. So this concave region, how could I build it? This concave region basically could be written as a product of 3 or 4 terms, y1 times y2 times y4 times not y3. So basically, it's not times. I'm sorry, this is not times. This is plus. This is plus, and this is and not this. And basically, I have a Boolean expression, and this Boolean expression involves AND operation and OR operation, and all of this can be done with a neuron. So a natural way to solve this problem is to just add a neuron. And a result of this neuron will be a concave region. So what I'm doing is I'm extending my architecture, and now I have a 3-layer structure. I have a 3-layer structure. So I have input neurons. And these input neurons, they split space using hyperplanes. So this is my input. Next, what I have is I have second layer neurons. And what they do, they find different convex regions. And these convex regions, for example, can overlap. And then, so this is the next part of my structure. And then I have neurons of the third layer. And what are these third layer neurons are doing is, for example, they are forming me regions that are concave. So I have a 3-layer feed-forward neural network. And 3-layer feed-forward neural network is theoretically capable of solving any data classification problem because there is nothing more complex than convex regions. If I have a classification problem, that means that I would like to tell where are the samples that belong to some class. And there is nothing more complex than concave regions that occupy these samples. There is nothing more complex in geometry. So theoretically, 3-layer feed-forward neural networks can solve any classification problem. So this is in qualitative terms. This is a qualitative analysis, but it gives you some intuition. What is going on in this network? Basically, the first-layer neurons do what they can do. They can only split a space with hyperplanes. What are the higher layer neurons doing? They are doing something like kind of a logic operations. Kind of a logic because we are having neurons that have this logistic function as an activation. So we don't really operate on binary values. We operate on real values, and flexibility also becomes higher of this analysis. So as we go up, we can say that we are shaping more and more complex decision region boundaries. They become more and more complex, and 3-layer is theoretically sufficient for solving a problem. But it doesn't mean that I cannot have 4 or 5 or 10 layers. It is also okay. If I can solve a problem using a 3-layer neural network, I can solve it with a 4-layer network, and so forth. And one more thing, just a terminological remark. If these neurons are perceptrons, if they are perceptrons, then a name for this structure is a multiple layer perceptron, or MLP. And the term MLP is being commonly used just for labeling or for naming multiple layer feed-forward neural networks, even if they don't have a step nonlinearity. So this is something that might raise some confusion, but just be aware that MLP means just a multiple layer feed-forward neural network. And it is more compact way of naming this structure, and that's why people commonly tell that, or commonly say that this is an MLP, even if neurons have arbitrary activation functions. It is not a name that is strictly following the understanding of what perceptron is. So MLP is informally used just to name multiple layer feed-forward neural networks. Okay, so just to conclude, what I have presented you is that a neural network is an idea for transforming data, transforming information in very general terms. And one of the purposes of this transformation could be data classification. So in data classification, I'm transforming input data onto labels, and that tell me what class is it. So multiple layer neural networks enable solving data classification problems, and in theory, they should solve an arbitrary problem. There are many other architectures of neural networks. Observe that this layer by layer transformation is something that was developed particularly to solve this classification problem. But if we are facing a different kind of a problem, then different architectures emerge. We will not probably have time on addressing other architectures, maybe, but it is not that certain. So we have a structure, and this structure is composed of several layers of appropriately interconnected neurons. And now what I would like to focus on is how to train a network, because this is the most important element in neural network theory and in practice also. Because a fact that I can qualitatively predict that it is possible to solve problems with neural networks, it is something that it is insufficient to make this paradigm really useful. I have to tell exactly how to train it, because I will be training neural networks, just like I was training a neuron. But now I will be training the whole network. And I will have examples, and I will have labeled examples, because this is a kind of problems that I am considering. I'm considering supervised learning. And I will tell you a little about unsupervised learning very soon. But now we are with supervised learning. So I will have a set of examples, training examples, and I will be presenting these examples to a network. And I will be trying to find a method for updating weights of all neurons in this structure, so that I actually improve, my performance improves. So let's consider a two-layer neural network. So let's consider, this is an input vector X. And assume that I have a two-layer network, so I will have neurons in the first layer. I will have, so here are neurons in the first layer. And then I will have neurons in the second layer. So I'm just providing so let's make it more symmetric, because it doesn't look very nice. Let's make it more symmetric, this drawing. So and I will have several connections. Obviously, there will be many connections here. So I will just show some of them to avoid clutter. And so let's assume that there are some connections here. And obviously, there are connections here. And these are outputs of my network. And let me use capital values for denoting neurons in the second layer. So the output will be Y1, and let's assume that I have M neurons. So the last output is Ym. Let's assume that here I will denote outputs using lowercase. So let's assume that I have a neuron, let's say K here. And so this is this neuron K, this is neuron 1, and let's say this is neuron N. And similarly, here is neuron number 1, here is neuron number M, and here is some neuron J. And let's assume that I have some input value L. So here I will have a weight. There will be a weight that connects a neuron K with the input L. And every element of a of output neuron, like every weight of this neuron will be labeled using a capital W. So this will be J and K. So this is a weight that connects a jth neuron's output input to the kth neuron output. And I will be given this structure. I will be trying to now consider what could be a rule for training weights of this structure. What happens? How information flows here? What I will have is I will have examples, and my example will be input sample. Let's say X alpha. Let's name it X alpha, and I will have some target. And target will be what I expect at the output of this network. My T alpha, it's a target value. Alpha will be just a vector of labels that I expect. And so for example, this will be 0, 1, and so forth, and 1. And it will have M elements because I have M outputs. So I will be having examples, and these examples will involve, in general, input vectors and target labels. And what I will be doing is I will be presenting X alpha to the input of my network. So I will present this alpha to the input of my network. And neurons of the first layer will compute their outputs. So a neuron number 1, Y1, will compute a value which is a nonlinear transformation of a dot product of its weights and X alpha. And the same will happen for neuron number 2, and the same will happen for neuron number K. It will produce a dot product of its weights and input vector alpha, and so forth. And once these values are computed, the outputs are passed to neurons of the second layer. And second layer neurons will compute their outputs. So the first output of the second layer neuron will be a nonlinear transformation. But now what I have this capital W times, and there will be a vector of outputs Y, and this vector of outputs Y is just a vector that contains Y1, and there will be YK, and somewhere at the end will be YN. So this is what will be produced at the output of the neuron number 1. And my neuron J, Yj, will compute output using, and here was 1. And here will be capital W transposed J times Y, and so forth. And what I will get at the output of my neural network is I will get a vector of actual outputs. And what I expect to get, so this is a vector of actual outputs, and what I expect to get is a vector of labels. So if I would like to tell how well performs my network, I can do it by introducing a loss function. This is a framework for analyzing the problem is exactly the same as previously. If I would like to make corrections to parameters of my system, and parameters of my system are weight vectors for all neurons, I need to first consider what could be the way of evaluating how well my algorithm works. And this evaluation will be done using a loss function. And the loss function should be reasonable. And a reasonable loss function could be, for example, a mean squared error. So what I can say is, okay, I can introduce a loss function. And this loss function will be a function of parameters. So theta is just that the theta are all parameters. So these parameters are weight vectors of first neuron in the first layer, second neuron in the first layer, and then is this kth neuron, and so forth, and then come neurons on the second layer, and so forth. So it will be my function, my loss function, and it will measure how well my structure performs for current values of parameters. So how well it performs? Well, I can say, since I have m outputs, I can say, okay, let it be just a mean squared error of actual outputs versus expected outputs. So I can say that this will be t I for this sample alpha minus yi for this sample alpha squared. And if it is supposed to be a mean squared, I can divide it over n. So this is my first approach, first initial phase of analyzing a problem. I need to derive a function that will be evaluating how well my algorithm performs, and my algorithm is parametric. So this objective function, this loss, also depends on parameters. And a general rule for learning is, if I would like to improve, I should take a step in a direction that is opposite. If I would like to minimize something, I need to take a step in a direction that is opposite to a gradient of this loss function with respect to parameters. So this is, if I would like to minimize something, I have objective function that is a loss. So it is reasonable to minimize a loss. So to do that, I should make corrections of parameters. So in general, this will be theta that are in an opposite direction with respect to a gradient of my loss with respect to this parameter. So this is a general statement. This is a general statement, and this statement is exactly the same as we were talking before when we are talking about training of any other algorithm. How to be more specific, and how to relate this general rule to a particular network that I have. So first, recall once again that it will be something that I will use in a while, that if I have a separate neuron, its weight corrections are ruled by a delta rule. So this is something that relates to a single neuron. I just put it aside because this will be helpful in a while. Let's assume, so I redraw the part of the drawing that I have above. So I have a neuron, jth neuron of the second layer. And what I have is I have a loss function, maybe just let's make it just a loss function. And this loss function is a mean squared error. And here I have, and assume that I'm presenting a sample alpha. So X alpha is a sample that is being applied to a network. So I have T alpha, I minus Y I alpha squared. So this is my loss function. And what I'm interested in is what would be the required update to a weight that connects J and K. So here is a neuron K in the first layer, and here is neuron J in the second layer. And now I'm interested in what should be an update of this weight to improve my performance. So basically, my question is, if my loss function depends on this value of this particular weight, if it depends on this particular weight, then I can say that I should take a step which is opposite to a direction of the derivative of this function with respect to this parameter. So this should be an update of my weight. So what I'm doing here is I'm doing something that I did several times already. I'm computing a derivative of my loss function with respect to a parameter that I'm interested in. And I would like to take a step in a direction that is opposite to this derivative. So what is a derivative of this loss function with respect to this particular parameter? In this loss function, observe that the weight wjk is present only in one term of this sum. It is present only because my loss is, let's skip for a while this 1 over m. My loss is T1 alpha minus 1 Y1 alpha squared plus T2 alpha minus Y2 alpha squared plus, and here there will be a fragment of this expression that involves expected and actual outputs at a neuron that we are interested in, because this neuron is the only neuron that contains weight wjk. Here, this term, and all the remaining terms do not have this weight. As they do not have this weight, derivative of L with respect to wjk for all these terms will be 0. So this will be 0, this will be 0, and the only non-zero is here. So what will be a value of this derivative? It will be 2 times T alpha j minus Y alpha j, and minus, I will just move to the beginning, and times, again, Y j is a nonlinear function of a dot product of its inputs and weights. So it will be a dot product of a vector wj times its inputs, and its inputs are just y's. So I can say that a derivative of yj with respect to w, so from that I can say that a derivative of this output with respect to j k is a derivative of this yj with respect to and this is Sj with respect to Sj times a derivative of Sj with respect to Jk. So if I would like to continue, this is just a derivative of my nonlinear function at a particular activation times, and here is a derivative of my dot product with respect to this particular weight, and the only term is yk here. So I can say that I can multiply this by f prime Sj times yk. So actually, you can see that the computations here are identical to computations that I was making for an isolated neuron. Because what really matters is whether I can identify an error, because once again, a delta rule for a separate neuron says that an update is proportional to what is at the input, what is the error, and here is a derivative of activation function. Now I have a network, but I am considering a weight to a neuron, and this weight affects only this output. If it is wrong, if this weight is wrong, so if this wjk is incorrect, its result is an error performed only here, and this error is target j minus yj. This is my delta. This is my delta. So observe that this is my delta, and basically I can say that an update of this weight wjk will be eta times tj minus yj times f prime sj times yk, because this is my error. I know this error because this is just a difference between what is expected and what is produced. I know this because I have computed this during so-called forward pass. When I was analyzing here this data flow, I did something that is called a forward pass. Forward pass means I'm passing information through the network upwards. So when I make these computations, for example, I compute what is yk. And if I have all this information, how can I use it? I can use it, for example, now to tell what should be an update to a weight of the output layer neuron. And this is basically just a delta rule. This is just a delta rule because I know the error, I know input, and I know what is the current activation, so I can compute this derivative. If this is a logistic function, is just yk times 1 minus yk. No, sorry. This is not this, but this is yj times 1 minus yj. So this is a derivative of my activation function. So just to conclude, because I am already okay. Let's continue next week. If you feel a little bit lost, I will at the beginning of next lecture try to repeat maybe more quickly this part, but we are in a process of developing a a rule for updating weights in a network, in a neural network. This time, this is a neural network. This is not just a separate single neuron. This is the whole network. But I began with the topmost layer, and I find that probably there is no difference. If I have a top layer neurons, the derivative of my loss function is independent on the remaining neurons. So this is from the point of view of a pure mathematics, but also it's quite intuitive. If I have an output which is composed of several neurons, and I'm concerned with one of these neurons, so an error that the neuron is performing is dependent on its weight, but any other neuron's error, it does not depend on that weight. So basically, if I'm considering updates of output layer neurons, I just can treat them separately, individually, just like I did with training of a single isolated neuron. So, and this is the simpler part, and a little bit more complex part will be provided during our next meeting. Okay, so that's it. And do you have any questions? I'm turning off recordings. Do you have any questions?